Force between multiple charges, superposition principle. So if there are if we have a multiple charge system, and if we want to find force on a single charge, then we use vector addition, and we take force on the particular charge because of each charge, and we add them vectorially. So that is what is called as superposition principle. So here we have q1 here, q2 here, q3 here, similarly number of charges, and q1 is here. So the distance between q1 and q2 is taken as r12, and q1 and q3 is taken as r13, and q1 and qn is taken as r1n. Now we want to find the force on q1 because of all these charges. So how it will be? It will be acting along the line joining the charges. So between the force q1 and q2, the force is in this direction. Okay, for q1 and q3, the force will be in this direction. For qn and q1, it will be in this direction. So F1, that is the force on charge 1, equals to F12, that is force on charge 1 because of the charge 2. F13, force on charge 1 because of charge 3. F1n, force on charge 1 because of charge n. So that is what is shown. F12 is nothing but kq and q2 by r12 square. So as we are writing in the vectorial form, I am using the unit vector. Okay, so similarly we have to add the forces in the vectorial format only. Okay, if similarly we want to find the force on the charge q2, then force on charge q2 will be F2, that will be equals to F21 plus F23 plus F2n, that is force on charge 2 because of 1, because of 3, and because of n. Then we have to use the respective charges and the distances between them respectively. Let us study about the next topic, equilibrium of charges. So if we have q1 and q2, two charges in this way, and they are separated by a distance a. Now I have to keep another charge q in between, in somewhere, okay, in this space, so that the net force on the q should be 0. Okay, if net force on q is 0, then the charge is in equilibrium. Okay, if its net force on the charge q, if the net force is 0, then it is said to be, then that charge is said to be at equilibrium. Now suppose if q1 and q2 both have same sign, what does it mean? If this is also a positive charge and if this is also a positive charge, then we have to keep the charge q in between the two charges, only then it can attain equilibrium. Why? Let us see that. Because of charge q1, okay, this is positive charge. Let us suppose assume q1 and q2 both are positive. So with this positive charge, what it will do? So this is a test charge, which is unit positive charge, we may take it as. So this is also positive, this is also positive, then it will repel in this direction. Okay, because of q1 it will have the force in this direction, and because of q2, again the q2 will repel q in this direction, so this force will be in this direction. So depending upon the distance between the q1 and q and q2 and q, at one point somewhere in between these two charges, the force on the q will be 0. So that point we can say the charge q is in equilibrium. So it is, so if we are taking somewhere outside, if we take the q on, suppose here let us take the q, because of, okay, now let us see, because of q1 it will repel q. Okay, so it will be in this direction, the force will be in this direction, the right side, and because of q2, again the force will be in this direction. So the forces are not in the opposite direction. If they are only in opposite direction, then they can cancel each other and the net force on q can be 0. But here there is no cancellation, so it is not possible. If both the charges are like charges, same sign, like charges, no it's not. If they are of same sign, then if we are keeping the charge only in between them, then there is a possibility of getting the equilibrium condition for that charge. If we are keeping it outside, then we cannot attain that. So that is what I have told. If they are with same sign, then you have to keep the charge between them. here we have studied about the equilibrium of charge. Okay, this Q, on this Q the force should be 0. Now let us take if they are of different sign. Yes, if they are of different sign, the charge should be placed on the side of the so the test charge should be placed on the side of the charge with lesser magnitude. Okay, if suppose this is plus 5 coulomb and if this is minus 3 coulomb, then we have to keep it on the side of this minus 3 coulomb. Only then we can attain the equilibrium condition. Okay, so if they are of different sign, we have to keep the test charge on the side of the smaller magnitude, the sign with smaller magnitude. If this is the distance a between the q1 and q2, and if we are keeping a q naught at a distance x from the q2, then it is just shown a plus x. So we'll see about this condition in the upcoming topics, and the questions also we will see. Now let us see what is equilibrium of a system. But for now, you please remember for these conditions where we should keep in order to get the equilibrium of that charge. Equilibrium of system. So if previously we have seen only charge Q was at equilibrium, but now if the whole system has to be in equilibrium, what does it mean? The force on any of the charges must be 0. Because of Q and Q2, the force on Q1 must be 0. Because of Q1 and Q2, the force on Q must be 0. Similarly, because of Q and Q1, the force on Q2 must be 0. Only then we can say the system is in equilibrium. So the net force on each charge of the system is 0. So that is what is called as equilibrium of the system. Intensity of electric field or electric field. So electric field is also called as intensity of electric field, whatever it is same, and it is conservative field, and the force is also electrostatic force is also conservative force. Please keep that point in mind. Now we are having two charges Q and Q naught. So let us note these points. Electric field because of point charge Q equals to kq by r square. So because of the point charge Q, because of this Q, what is the electric field because of this Q? That is kq by r square. You have to keep this charge, okay, because we are finding electric field because of this charge. So we have to write kq by r square. What is the force on Q? What is the force between them? Because here there are two charges and they are separated by distance. Suppose it is r. Then what is the force? Kq q naught by r square. Either it is q or either it is q naught. The force on both of them is equal only. Kq q naught by r square. Now what is the force on Q naught? I have told it is kq q naught by r square. So this I am writing it like this: kq by r square into q naught. So this kq by r square is nothing but the electric field because of this charge q, and that I am representing with it E into q naught. So what does it mean? So if there is a charge q naught placed in an electric field E, then we can find the force on that charge q naught by multiplying the electric field and that q naught. So please try to understand. If electric field intensity E at a point in an electric field be known, then we can determine the force F acting on the charge Q placed at the point. So that is what I have already told. So if we know the value of electric field in that region, and if we keep a charge Q naught in that region, to get the force on the Q naught, you have to just simply multiply Q and that electric field, Q naught and electric field. Okay. So this I have shown for a general condition. Force is equals to Q into electric field. Now what is the direction of force? Before that, I wish to say one more thing. What is the direction of electric field? So electric field, it originates from the positive charge and it goes towards the negative charge. Please remember, if this is the direction of electric field, then you can assume the positive charges are accumulated in this side and the negative charges are accumulated in this side. Okay, this you have to remember. If this is the direction of electric field, if this is the direction of electric field in the right side, towards right side, then this side it will be positive charges, only then because of that there will be electric field, and to the negative charge the electric field will be going inside toward, it will take towards them. So that is the direction of electric field. Please keep that point in mind. So what is the direction of force? Now if we are keeping a positive charge q, okay, if this q is positive charge, then what will be the direction of force? The direction of force is in the direction of electric field. Let us see the reason. If I am placing this q in this electric field, then this is a positive charge, this is also positive region, so definitely they will repel. But this is negative region, so it will attract the positive charge this way. So the force is in this direction, that is towards the right side or in the direction of electric field. If q is negative, if this charge is negative, then this minus and this minus it will repel, this minus will repel it, but this positive will attract. Okay, so the force on the negative charge will be in this direction or in the direction opposite to the electric field. So that is what I have shown. Now we know electric field, so F is equals to E into Q, that means E equals to F by Q. What is the unit? Unit of force is Newton, unit of charge is Coulomb, so it is Newton per Coulomb. And let us see the dimensional formula. For force it is mLT power minus 2, please remember that. And for Q is nothing but a charge, so charge is equals to current into time. So for current it is ampere, for time it is t, so that is what is written A into t. So that is equals to m L t power minus 3 a power minus 1. So that is the dimensional formula for electric field. So let us see one more case. If this is the direction of electric field and here there is a positive charge, we know the weight mg acts downwards because of this positive charge must have some mass, so that mg will act downwards. And if this is the positive charge, then what is the direction of force? It will be in the direction of electric field, so that is QE in the direction of electric field. If this is a negative charge and if this is the direction of electric field towards down, then this will be the direction of weight, that is mg, and QE it is in the direction opposite to the electric field. Okay, that is QE in the upward direction, and this charge will be at equilibrium when QE equals to mg. Okay, then this charge will be in equilibrium because the forces balance each other. So QE equals to mg. From this we can determine Q equals to mg by E, or whatever we want, whatever depending upon the question we can use it like this. Electric field due to point charge q, we have just now seen it, E equals to kq by r square. If because of charge q it is the electric field, it is obeying inverse square law. Please note it, E is inversely proportional to r square, so it is obeying inverse square law. And this is the graph between E and r. Okay, it is like this. Now point charge produces electric field spherically symmetrical. The value of electric field intensity at a given distance from the point charge in all directions is same. So if there is a positive charge, let us suppose there is a positive charge, then the field because of it will be radially outward. Okay, and it will be, we can assume it is in the spherically symmetrical. The field there we can, if we are taking its field, you can imagine here it is shown as a circle, but it will be in the upward direction, it will be in the downward direction, everywhere. So it is like a sphere, please note it. And if we are taking at this point, okay, if it is at certain distance from this q, if this is at r, then even if this point is at distance r, this in this point which is at distance r from this q, so the value of electric field and this point and this point will be same. So that is what is told, please remember this.